So hi, this is the fourth and last example of chapter 5.4. It is question 102. This question is quite unique, so let's read the question first. Question 102. A light bulb is placed 80 centimeters away from a screen. Where should we place a converging lens if we want to obtain a clear image on the screen? Given that the focal length is equal to A, 10 centimeters, and B, 20 centimeters. We will see that we have a lot of algebraic step here. So the first thing we need to notice is, well, first having a look at the diagram, we are told that there's a distance d1 between the object and the converging lens, and there's a distance d2 between the object and the surface or the screen where we will project the image. Now, there's an important point here that we need to realize is d1 over here is basically the distance of the object. The distance of the image, therefore, has to be 0.8 minus d1. So di is equal to 0.8 minus d1 or 0.8 minus do. All right. Now, let's write down the distance formula and we will see that it's a bit tricky here. So we will replace the distance of the image because the goal is to find the distance of the converging lens. So we want to get rid of that value over here. So we got 1 divided by do plus 1 divided by the distance of the image. We replace it with that term over here. 0.8 minus do. And it's equal to 1 divided by f. Here we have to do an algebra trick. Basically, we have to take the denominator over here, multiply it by the numerator and denominator over here, and take the denominator on that side, multiply it by the denominator over here, and the numerator on that side. Let's see what it looks like. So 0.8 minus d0. Now note, because these two terms are not on the same denominator, we can combine them. So we got 0.8 minus distance of the object plus the distance of the object. These two terms will cancel out. So we get 0.8 divided by do, 0.8 minus do, and this is equal to 1 divided by the focal point. All right. So at this point, I need more room, so I'm gonna start erasing all of this, giving you a second to pause the video, write down the relevant information, and then I'm gonna erase to get more space. All right. All right, so we need that formula over here. 0.8 d 0.8 minus do, and it's equal to 1 divided by the focal point. Now we can erase that one. All right, so let's flip that the focal point on that side, the denominator on that side. We distribute that term over here. This is actually do, sorry. We distribute the distance over here, so we get 0.8 f is equal to minus d0 square plus 0.8 do. Now just to make sure the square is on that term over here. We take these two terms and we flip them on the other side. We get do square minus 0.8 do plus 0.8 f is equal to 0. Now let's make a small conversion just to highlight the type of formula we have here. Let's replace dO by x. If we replace dO by x, we get this formula instead. And this is a quadratic formula, all right? So I'm gonna give you again a moment to write down all these steps. You can pause the video. Again, I need to erase the board to continue that step. All right. So we got x squared minus 0.8, x plus 0.8 multiplied by the focal point is equal to 0. The goal here is we want to use the quadratic formula. Now, in the quadratic formula, we use the constant in front of the quadratic term to be our a term. This one is our b, so b is equal to minus 0.8. c is equal to 0.8 multiplied by f in this case. Now remember that the quadratic formula is the value for x which this complete formula becomes 0. So it's equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So let's write down. We get minus 0.8, so we got 0.8 plus or minus 0.8 square minus 4. The a is 1, so let's not write it. It will simplify our life. Multiply by 0.8, multiply by the focal point. Divided by 2, multiplied by a, so we get that formula over here. All right. So again, I'm going to ask you to pause the video, write this down. We will use that formula with the different focal point to find what is the value, what is the distance of the object necessary in order to create a clear image. All right, so I'm going to erase that part. X. And actually our x here, it might be more intuitive to simply replace it by d1, so x is equal to the distance of the object is equal to d1, which is the value we're looking for from the beginning. By the way, we take 0.8, we divide by 2, and simplify over here. Okay, so for part A, we are told that the focal point is equal to 0.1. So if we input 0.1 here, we get two values. We get d1 is equal to 0.683 or d1 is equal to 0.117 meter. In both cases, they are meter. So that means if the distance between our object and the converging lens is equal to 68.3 centimeter, we will have a clear image. And if the distance is 11.7 centimeter or 0.117 meter, we will also have a clear image. Now keep in mind, the magnification won't be the same for both of them, but in both cases, they will create a clear image. All right? Let's have a look at part B. What happens if the focal length is equal to 0.2? This one creates something interesting. So let's plug in the value just to highlight that part. So d1 is equal to 0.4 plus or minus square root of 0.8 square minus 4 multiplied by 0.8 multiplied by 0.2 divided by 2. Now if you look here, 4 multiplied by 0.2 is equal to 0.8. So we have 0.8 multiplied by 0.8 the two terms are equal, so we get the distance is 0.1 meter. In this case, we have only one, for a focal length of 20 centimeter, we only have one distance where we will get a clear image on the screen, and it's 40 centimeter. Actually, it's right in the middle. So in the first case, because this term was not 0, we had two locations where we could create a clear image. For part B, we had only one location. Now, an extra question that is not asked in question 102 is, what happened if the focal length, and by the way, there's a meter missing here, if the focal length become higher than 0.2? That's a question you will have to answer in the second lab. All right?